optimal location problems with routing.
Okay, it is always a pleasure to be here at Newton Institute, and I wish to thank the organizers for the invitation. I will present something maybe not strictly related with the mainstream of the workshop. Nothing of extreme will be in my lecture. The problem originated by some discussions with some colleagues in aerospace engineering department of my university, and together with two PhD students we did this project. Serena Guarino, PhD student in mathematics, and Fabrizio Olivero is a PhD student in aerospace engineering. So the problem, roughly speaking, is to design a very efficient network to transport by airplanes, to transport a very big amount of resources at a long scale, at a low price. So this is the big idea, and this big idea has this problem has two phases. First phase is more technological, is more for engineers. Design new types of airplanes, planes which are able to carry big amounts of resources and can fly for a long distance at a low price. So this is an engineering, a technological problem. And the second one is a mathematical problem: design the network, where you should put the airports. So this is a more mathematical problem. And the coupling of these two sides could give very interesting issues. Concerning the first one, the engineering problem, you can't believe how creative are our colleagues engineers. They are really very, very creative about the new shapes of airplanes. How can they fly? Just to show you some picture, this is called airship. You see, this can carry a big amount of loads. This one is Boeing Pelican. I don't know if they fly. This is projects, but the last two I will show you, they actually fly. I saw them. This has been developed in Delft, Technical University of Delft. You see, this is a kind of brand plane with the wing folded. And the last one, this has been developed in my university. This is another kind of brand plane, and this one I saw, it really flies, and also very well. So this is concerning the engineer. This is their job. Let us now concentrate to the mathematical problem. So the mathematical problem is to design the airport, where we should put the airport once the resources density rho of x is known. So assume we know perfectly the location of the resources. You can imagine a carrier like DHL, FedEx, or UPS. And they know very well how the resources are spread over the region they want to cover. Rho of x is the density of resources. And the problem is they have to do two things. First, they have to concentrate the resources in some points. And so this is a transportation problem at a small scale. And then they have to connect all these points. The points are the airports. They have to connect all these points by airplanes. So this is two-level optimization. So the data are the given region omega. This is known, this is given. and the resources density rho of x. So they are perfectly known. And also a given integer number, capital N, which is the number of airports so this is some financial constraint, so the number N is prescribed. You have to decide where to put your airports. So this is two-level optimization. The first one is very well known in the literature. This is called the pure location problem. The location problem means the following. We have the rho of x, and we have to concentrate the rho of x in a number capital N of points. So the points are not known, and we have to find the points in such a way that the concentration procedure is as cheap as possible. And so to measure the cost of this concentration procedure, a very good quantity is a Wasserstein distance. And so the mathematical problem is this is the cost, L of sigma. Sigma is the unknown, is the n points. The set of n points I call sigma. And so this is the minimization problem for the pure location problem. Find a sigma in such a way, this Wasserstein distance, so the work of concentration, the resources in points, is as small as possible. So in the practical problem, this is done by small trucks. Small trucks, you can imagine UPS or DHL. They use cars or small trucks to concentrate the resources. The resources are letter or packages, small packages, and so on, in some points. So this is a pure location problem. But also this pure location problem is very simple to state, but is tremendously difficult to solve. And let me explain, so this is another formulation, equivalent formulation. You minimize the average distance. This is a very natural quantity to be minimized. The average distance from the points you have to choose. So why this problem is so deep? Of course, if the number L is small, let's say 10 or 20, every computer can do it very quickly. But as soon as this number becomes, say, moderate, of the order of 50 or 100, the problem is NP hard. And so you will need really a lot of time to solve it. The reason is very simple, because the cost function involves n variables. Each variable has two coordinates, so 2n variables. But the cost function has a huge number of local minima, really a huge number, like factorial n. And so if you launch a very quick method like gradient method, all of them are very quick, you will end up in a local minimum. In local minima, there are a lot of them. And so this is the reason why the problem is so hard to solve, even the pure location problem. Of course, we know there are global minimization problems, Monte Carlo and so, but all of them are very slow. This is the question. And so no hope to solve this problem as soon as n is moderately high. You can imagine you want to distribute, you want to choose in a town, in a big town, where to put gas distributors. It's the same problem, location problem. Where to put the gas distributors in a town, in a big town, and assume you want to distribute, say, 100 gas station in a town, or pharmacies or whatever. Maybe in England should be pubs, 100 pubs in a town, in such a way that the average distance is minimal. So this is a very, very difficult problem if the number n is of this order of magnitude. On the contrary, when n becomes very big, the problem becomes again simple. So this is very interesting philosophy. Small n you solve very easily by computer. Intermediate n, the problem is very difficult. Very big n, you develop an asymptotic analysis, and then the problem again becomes simple. In the asymptotic analysis, you don't find anymore the points, but you find the density of points, the density of gas distributors, not the precise location of gas distributor. This is the philosophy of this. And this is well known in the literature. And instead of looking at the precise discrete problem, you put a continuous variable, which is the density of the points, and so you end up to determine a limit cost function, which is this one. You can prove that the limit problem is this one, where mu of x is the density of the concentration points, not the precise location, but only the density. And so you see, this is the limit problem, and this problem is very easy to solve because just minimize this under the constraint that the integral of mu of x is 1, and this is a very simple solution, and this is the optimal distribution. This is quite interesting to look at this formula, because you see, if you double in a certain area, if you double the density of population, rho of x, let us speak in terms of pubs, for instance, in a certain area of the town, the population is double, then you don't have to double the density of pubs, because you see the exponent is a concave function. Take, for instance, a dimension 2 and p equal 1. So this is a square root of rho. So the good distribution of pubs should follow not the distribution of population, but the square root of the distribution of population. This means that this gives some advantage to less populated parts. So instead, in our coupling location and routing, I will show what a routing cost is. Instead of considering the difficult discrete cost, let us replace it by this asymptotic continuous counterpart. So instead of the location term, we use this, where n is the number of airports again, c is the constant which appeared in this asymptotic analysis, and this coefficient a is just a coefficient which takes into account the technology of trucks. So given a certain kind of truck, this provides you the coefficient a. And so this is the continuous cost function. So this is a plot of this constant Cp2. You see, this constant does not change a lot. So it is more or less constant. It changes very little in terms of p. So you see, if p is between 1 and 2, it's pretty constant. So what about the routing cost? Now you have your points. You have to connect them pairwise. So here I will do two important simplifications, because if not, the problem is too complex. First, the transfer between one point to another is made according to what is called point-to-point connection, just like Ryanair. No intermediate scale, no intermediate stops, just point-to-point. So if you want to go from an airport A to another airport B, you go directly without any intermediate stop. This simplifies a lot the problem. So the first simplification is this point to point, and the second one, which is more severe, is that the cost of the flight does not depend on the weight you are carrying. So this is why this model is very good for a carrier like UPS, FedEx, or DHL, but is not very good for a passenger company, because in a passenger flight, there is a big difference if you fly with the empty airplane or with an airplane full of people. The cost is considerably different. On the contrary, for these carriers, the real cost is the cost of the flight. This depends very little from the weight they are carrying on. So this is a second simplification. And then if you put all together, you summarize, you end up with this cost. B is a constant which depends on the kind of airplane you are using. So this is a technological constant. And then you connect all the points pairwise. So this gives you this sum to some exponent q. And so if you want to, again, rephrase this in a continuous way, you should write in this form, where mu is a density, again, of points. And so this is a picture of what happens in reality. You see the cost of the airplane is concave. I mean that this exponent q is less than 1. And this is very reasonable because in airplanes, the big cost is the takeoff and the landing. The cruise is less costly than the rest. So this is simulated by this blue curve. On the contrary, the small scale transport here is linear, but actually is even convex. The profile is even convex, so this green line should be even convex, which means that the exponent p is bigger than 1. It is easy to understand why the cost should be convex, because on a small scale, if you go farther, you should pay, I don't know, the meal to the driver and overnight to the driver, and so the green line here is linear, but could be even convex, but never concave. And so this explains why at a small scale it is better to use these small trucks transport. At the longer scale, it's better to use airplanes. So again, this is the total cost if I put together the pure location plus the routing cost. So the goal is to minimize this. This is a continuous counterpart. The goal is to minimize the sum of these two terms over all distribution mu of x and probability mu of x, right? Density and probability mu of x. So this is the problem. And you see this is a nasty term because it's a double integral which provides a convolution operator. So if you set epsilon this quantity, so n is a number of airports quite big, so epsilon is quite small, but not very small. Small, but not very small. So you end up with this functional, where this is the leading part, which is the routing part, and this is the small scale location term with an epsilon in front. So now, again, the idea, this problem is also NP hard. I don't want to solve it because I would need the centuries of computer time. And the goal is, on the contrary, to study the asymptotic limit and then to see what the asymptotic limit says. So the asymptotic limit when epsilon goes to 0, which means when the number of airports is pretty big. And so this can be done. This can be done, and well, the procedure is quite well known. You have to estimate the order of vanishing, because when epsilon goes to 0, everything vanishes. first you have to estimate carefully this order of magnitude, then you have to rescale the cost, and then you have to pass to the limit to the rescaled cost. So this is three-step procedure, and in this case it can be done, and this is what we obtain. So the order of magnitude can be estimated very carefully, and it is epsilon to a certain power, which is 1 over 1 plus p over d. This is the first step. Second step, you have to rescale the cost. This does not change the shape of minimizer, just a rescaling argument. And so you have this, where you have a small coefficient here and a big coefficient here. And finally, you have to pass to a limit, or if you want to, you have to solve the Euler-Lagrange equation of this one, because this is what I am interested. The main variable here is mu, because mu is the density of distribution of airport in the given region omega. So if you want to solve this, write the Euler-Lagrange equation, which is this one. You see here you have the convolution operator. So this can be done recursively, and second procedure is just jump and pass to the limit when epsilon goes to 0. And this can be done quite easily, and this gives you the limit cost. Well, it is clear to understand that the limit, the best is to concentrate everything in a single point. In a single point that you can see more or less like the main hub of the system. And the cost of this point is this one, is a constant, times you see this kind of average, is a kind of weighted barycenter of the rho. Rho to some power beta and x minus x0 to another power. So if you minimize this limit cost, this gives you the best location of the main hub. And then you spread the rest of your density according to this equation. So this is the idea. So mu epsilon, the asymptotic form of mu epsilon, is a Dirac delta in the main hub with a quite big coefficient plus a kind of cloud of small airports around, and this cloud is epsilon to the beta, which is a very small weight, times this phi. This phi gives you the weight you have to, the way you have to spread over the small airport around the main hub x0. So this is very nice. We try to do some numerics of this. This is a toy, very simple 1D problem. So the red line is a rho, just two level, rho equal a coefficient and rho equal another coefficient. So an interval in two parts. And then you see the best location is the top of the blue line. So the best location on main hub is here. These are different values of epsilon, you see here. We tried some more complicated 1D situations. Again, you see the red line is rho. There is a very high peak here, but you see if you compute carefully, the main hub does not follow the peak. The main hub, you see, for instance, the black line, the top is here. So of course the black line feels the big peak here, but there is a kind of average, and the main hub is located here, 0.2, at the top of the black line. So this is very interesting. We tried a more concrete situation. We took the US region, the region omega is the US. And what is rho? Well, my colleagues engineer told me that the rho, the density of resources, is very close to the function which gives you the local income, the income in terms of money. And so this is proportional to the resources DHL could carry on. And so you see more money on the East Coast, in California, very little in the middle. So this is the raw vex of the US. And then we launched our algorithm to see what happens. And we got this. This is the corresponding mu epsilon. For epsilon small, but not very small, according to a certain number n, because you remember epsilon was linked to the number of airports. We took the number of airports around 100, and we compute the mu epsilon, and the mu epsilon has a peak here, in this part, in the middle of nowhere, here. So, according to our algorithm, the best location for the main hub should be more or less here. And then we did the limit plot. The limit plot moves a bit on the west. This is the limit plot. The limit plot gives, this is epsilon equal to 0. Epsilon tends to 0. Gives these are the level lines of the density, and this is the you don't see here. I see better the shape of US here. Gives this, which is moved slightly on the left with respect to this. Well, this seems to be in the middle of nowhere, and we said, well, but what the real companies do? And we checked what the DHL, UPS, and FedEx do. So remember this picture. And this is what happens in the reality. So DHL in Cincinnati, Ohio. UPS is Louisville, Kentucky. And FedEx is Memphis, Tennessee. So quite close to this forecast we did. And I think I can stop here. Thank you very much for your attention.
Questions or comments? Yes?
Can I ask a question about this very last point?
Yes.
Because the companies seem to be very close to what you calculated. So how did they decide to sort of...
This is a good question. I don't know. It should be, I can imagine a historical reason. They move something like dynamical. They started somewhere, they move slightly. Should be very complicated, I guess.
Yes?
Or maybe they have a similar algorithm, I don't know.
You mainly look for the efficiency. What about stability?
This is another story. This is just the optimization point of view, of course. This is very interesting to see how things can move with small perturbation. This we did not perform.
Small.
Yeah.
Think about extreme events.
Yeah, of course. This gives a link with the workshop.
Yes?
Wouldn't be the cost function for airplane transport convex as well, because you have a big cost taking off, going back to the same airport, and also at the upper limit, basically the airplane is carrying only fuel and no payload, so basically the cost goes to infinity.
Well, but this is what I learned by my colleagues engineer. But in a flight, most of the flight of a medium range, like in the US could be, most of the cost is the taking off. So this is why this blue curve was concave. This is the main reason. The cruise cost, well, there is some cost, but is nothing with respect to the taking off.
Michael?
Yeah, just a personal remark. I was very surprised when I visited Pisa to find out that, well, Florence and Pisa, that the main airport in Tuscany is Pisa,
Yes,
not
indeed.
Florence.
Now this is
I assume it's for historical reasons.
no. This is for geographical reason because Pisa is flat and Florence is. There are a lot of hills in around.
Yes, regarding this, so it seems to me very well suited also to study problems of ecosystems, basically. So you can study the evolution of ecosystems, the application of it.
Well, the location model applies to an enormous number of situations.
Transport of pollens, you know, like
Indeed. Let me mention to this respect that there is another more complex version in which instead of locating points like gas distributors, pharmacies, pubs, in Italy maybe churches, you locate pipes. So one-dimensional objects. So you want to design a network of pipes of water, of electricity cables, or internet fibers. This is similar. Problem is similar, more complicated because objects are not zero-dimensional like points, but one-dimensional lines. So in this respect, this model applies to enormous number of situations. I'm sure even in economy.
Well, thank you again.